The last theory on exponential and logarithmic functions is a process called logarithmic differentiation. That might sound like the derivative of a logarithm, but it's not. We're going to use logarithmic differentiation to find the derivative of a function that has another function as its exponent. What would that look like? How about y is equal to, maybe x is a pretty basic function. What's the easiest function we could use as an exponent? I suppose x. What else could you have? Maybe a base of sine of x with an exponent of cosine of x, right? A function that has a function as its exponent. Now, I suppose x to the power 2 fits the description, but you have an easier way to find the derivative of x to the power 2. Let's make sure you understand when you're using logarithmic differentiation and when you should do something else. What does x to the power a look like to you? Well, to me, it looks like x squared, x to the 7th power, things like that. If a is a constant, heck, we could be thinking x to the power -3. All functions of this form, we can use the power rule for. Positive exponents, negative exponents, rational exponents, so long as the base is a variable. So in a case like that, how do you take the derivative of x squared? You use the power rule, 2 times x to the first power. So the derivative of x to the power a to the power, a times x to the power, a minus 1. Just using the power rule. And you use the power rule to find the derivative of constant with an exponent of x. Let's think about functions that take this form. How about e to the power x? Do you use the power rule there? Of course not. 2 to the power x. You don't use the power rule there either. What's the derivative of an exponential function? Well, that's going to be the derivative of a to the x is a to the power x, natural log of a, so long as that base a is positive and not 0, not 1. Although I suppose by saying positive, 0 was already off the table. What about the derivative of a constant with an exponent that's a constant? Let's think of some of those. How about 2 to the power 2? 4 to the power 4. Are you getting it now? The derivative of a to the power a is 0. The derivative of any constant is 0. All right, this is what we were looking at. X to the power x, a function is a base, that's x, and a function that's an exponent, that's the other x. Can we use the power rule like on x squared? No. The power rule works when the base is a variable and the exponent is constant. That's how. Can we use the derivative of an exponential function rule, like 2 to the power x? No. This rule only works when the base is a constant and the exponent is a variable. And we also know that x to the power x isn't a constant. That's a variable with an exponent that's a variable. So what do we do? Well, we rearrange so that we don't have a variable base with a variable exponent. If you want to get to an exponent, you use a logarithm. What logarithm do you choose? I choose natural log, mostly because it has the easiest derivative. You could use any logarithm you want, but the derivative of natural log of x is 1 over x. I don't have to worry about natural log of the base or something. So when I have a logarithm, I'm allowed to move the exponent on the number inside the logarithm to be the coefficient of the logarithm, which is what I've done, which means now I don't have that problem x to the power x anymore. I just have some other function that apparently shares most ordered pairs. We'll worry about domain later. So I'm going to need the derivative of natural log of something. I'm going to need the derivative of x, that's super easy, and I'm going to need the product rule. So the derivative of natural log of something is 1 over that something. Our something is the function y, so we're going to have to multiply by y prime, the derivative of y. On the right-hand side of the equals sign, we need to use the product rule. And the derivative of a product of two functions is the first function times the derivative of the second function plus the second function times the derivative of the first function. All right, well, we have a derivative notation y prime, so let's rearrange, multiply both sides by y. So the right-hand side ends up being y times 1 plus the natural log of x. A little bit weird to have that y, so we'll replace y with way up top, x to the power x. And distribute to get the derivative of x to the power x is x to the power x plus x to the power x times the natural log of x. Let's do that process again. Maybe we can use an easy rule. Product rule? Oh, not the product rule. The power rule? No. X is definitely a variable base, but sine is not a constant exponent. And we know x to the power sine of x isn't like e to the x or 2 to the x. So we must need to rearrange, get rid of that exponent sine of x. Use a logarithm so you can use that property where we move the exponent of a logarithm to be the coefficient out front. Do you remember why I choose to use natural log? In calculus, natural log has the easiest derivative of all the other logarithms. So you move that sign out front, and now you have natural log of y as the product of sine and natural log. The derivative of natural log of y is 1 over y times the derivative of y. And the derivative of sine times natural log of x is going to require the product rule. So the derivative of a product of two functions is the first function times the derivative of the second function plus the second function times the derivative of the first. Go ahead and solve for y prime. Multiply both sides by y. And I'm going to write this as sine of x over x, that's a little prettier, and then natural log of x cosine of x. Maybe I'll put natural log in parentheses. One last thing, I'm going to do this in 2 steps. I am going to multiply x to the power sine of x times sine of x over x, and then x to the power sine of x times the natural log of x times cosine of x. That was really ugly. All right, one last example. Since we have a base that's a function, cosine of x, and an exponent that's a function, sine of x, we're going to have to rearrange our equation so we no longer have that situation. Take natural log of both sides of our equation. And move that exponent sine of x. And then now it's time to differentiate. The derivative of natural log of y is 1 over y prime. The derivative of a product of two functions is the first function times the derivative of the second function. Oh, the derivative of natural log of something is 1 over that something. Our something is cosine, which has a rate of change of negative sine. Did you get lost in there? Okay. Remember, we were actually doing the derivative of a product of two functions. Sine was the first function. This 1 over cosine negative sine is the derivative of natural log of cosine of x. So first function times the derivative of the second function plus the second function times the derivative of the first. The derivative of sine of x is cosine of x. All right, one last thing. Y prime is going to be y times all of this stuff. Let's do that in one step. So y is equal to cosine of x with an exponent sine of x. So I'm replacing y with that and multiplying on both sides. And then what goes in here? Sine times negative sine is negative sine squared over cosine. Maybe there's a better way to write that. How about negative sine of x tangent of x plus cosine of x times natural log of cosine of x. I just put this cosine first. All right, I'm sure you can find other examples on your own to practice. Thank you for watching.